Hello, good morning and welcome everyone back to CS300 Introduction to Algorithms. And today we're going to resume our last session talking about string problems and string algorithms. But first of all, let me pose the question for today's attendance quiz in the chat channel. So here you are. This is your question for the quiz question for the attendance check. Right, and that being out of the way, let me now resume and start the slides. Yes, here we are. So, yes, we are here to talk about string problems and string algorithms. So the syllabus is to first recall terminology, mathematical notions related to strings. Then we will talk about pattern matching problems and pattern matching algorithms following our paradigm or virtue of separating problem specification from problem solution. And similar, we're going to talk about another class of problems, the substring problem, the longest common substring problem, and devise and analyze algorithms for that problem. Then we talk about edit distance problems and devise a dynamic programming algorithm for that problem. We talk about formal grammars and about context-free parsing with a polynomial time Koki-Younger-Kasami algorithm. And then we talk about string compression, specifically Huffman compression, which is a famous lossless compression algorithm. Okay, so that being said, the terminology thus being said, here is the terminology for strings. So we fix a finite alphabet. Often it's the alphabet of bits, so 0 or 1. But other alphabets like the Latin alphabet or Hangul alphabet are also popular choices. The important thing I'd like to stress here is it should be finite, so that every single processing of one symbol from the alphabet can be counted as taking constant time, so that the size of the alphabet can and will be dropped from our cost analysis of the algorithms that we devise will be discarded in the big O asymptotic notation, where constants can be ignored. Now, a string over this alphabet is defined to be a finite sequence, again, finite sequence of elements from that alphabet. And we use star to denote that this is an arbitrary but finite Cartesian product of this alphabet, right? So if we raise the alphabet to the nth power, then that means n-fold Cartesian product. It means that it means that we're talking about strings of length precisely n, and the star indicates that we're talking about strings of arbitrary finite length. And in order to express the length, the arbitrary but finite length, we use the vertical bars as terminology. So vertical bar around the string indicates the length of the string. And let me also emphasize that we start counting the symbols in the string with 0. So that's our common convention in computer science to start counting with 0, and array indices started with 0 as in C. And indices or strings start with 0, so that a string of length n actually consists of symbols with index ranging from 0 to n minus 1. So that's a terminology for strings. And if we have two strings, then we can concatenate them to form a possibly longer string, and this small circle is used to denote this concatenation operation. The initial segment of a string is denoted with this small, strictly less than m symbol attached to the string. So if we have a string of length which is at least m, then we can kind of cut off the string at the mth symbol, so that only the first m symbols remain. The mth symbol is, remember, since we're counting with 0, the m symbol is already exceeds the length to be m, and therefore we cut off there. Yeah, that's an abbreviation that we'll frequently use. Also, we use the substring notation. So a substring is a string that occurs in a given string consecutively. That's important thing to stress here. So a consecutive sequence of symbols that occur in the string with a prefix possibly and a suffix. That's a terminology for the string and substring. And the initial segment of a string is a substring that starts at the beginning of the string. So yeah, later when we talk about grammars, we will need some finite set of variables, and those variables should be different from the characters of the string. And this is denoted with the set V, which is a non-empty set of variables that is supposed disjoint to the alphabet. Okay, so that's this. And now we start talking about the first string problem, namely the pattern matching problem. So the pattern matching problem is the following. We're given two strings, and one string is supposed to be very long, much longer than the other one. And the other one, the short string, that imagine this to be the pattern, right? We want, for example, we have a very long novel, right? Like by Thomas Mann, and in that novel, we want to find all occurrences of a certain character. So the name of that person will be short compared to the length of the novel. So think of W as the novel and P as the name of the character that we want to search in that novel. So that when we analyze our algorithm for that problem, actually both parameters will be relevant, but the n is going to be the larger one, generally speaking, than m, where m is the length of the pattern. Right. And from a computer science perspective, the strings are provided, are input in forms of arrays. Yeah, as usual, from 0 to n minus 1 for the long part, for the novel kind, and index from 0 to m minus 1 for the short. And the question is, does the long string contain somewhere an occurrence of the short string? That's the first variant of the problem. And that's kind of a decision problem, right? So here in this perspective, in this specification, the answer will be yes or no. Whereas in the second case, we're interested in the first occurrence, right? This is, by the way, this is something you do all the time in your text processing software, right? In your editors or in your text processor. Hancom Word or Microsoft Word or Open Office or whatever, right? So this is really an important and very basic problem. And we want to solve that efficiently because, I mean, yeah, common text corpuses easily have n equal to 1 million, right? 1 million characters is pretty common. So, right, so let's search for the first occurrence, or another variant of the problem specification is to ask for all occurrences. However, the latter problem variant has its kind of disadvantage for our algorithm design and analysis endeavor, because when there are many occurrences, then that means our algorithm will have to output many things, right? So that might happen that the algorithm is spending all of the time just outputting wherever an occurrence has been found. And then simply the output is what takes the time. And that's not really very interesting, to be honest. What is more interesting is the first occurrence problem, because in that case, the output will simply consist of one integer, so that the bottleneck, the most of the time of the algorithm is more likely to be spent for the searching than for the output part. And this is where we can really improve the efficiency. If the output is very long, since it's required to produce all possible occurrences, then there's no chance to improve the efficiency, and that's not something, yeah, that we kind of have to give up. No hope in that case. But also in the first case for the decision problem, the output, the answer will be just yes or no, one single bit, and therefore it doesn't really take much time for that, and the most of the time will be spent for searching, and this is where we should well put our efforts in solving that. Right. So here's an example, artificial to be fair, but still illustrative. Yeah, purposely designed to be illustrative. So the example is the following. Here we have a string ABC, X, ABC, D, AB, X, ABC, and so on. So this is the alphabet is like 5 characters, A, B, C, D, E, X, right? A, B, C, D, E, X, and 6 characters. Yeah, I'm bad at math. Anyway, so that's a kind of text body. And in that text body, we're looking for the following pattern, A, B, C, D, A, B, D, right? And why is that illustrative? Yeah, let's return to that question when we have discussed the first, the naive algorithm. The naive algorithm will simply test all possible pairs, right? All possible pairs of output or configurations where the pattern could occur in the given text string, in the given string. So the pattern could occur anywhere. So we're looking for all possible starting positions, K, as indices to the long input string, and check whether in this position the first character agrees with the first character of the pattern. This is this test, right? So this is the first character of the pattern. See whether this agrees with the current character at the string, and if so, then compare the remaining characters of the pattern, whether they also occur in order, in sequence, in the input string. So compare the next character and the next character and the next character in the input string to the next character, next character, next character in the pattern. And if also these agree, then we have a match, right? Then output K, the index of the input string of where the first match happens. So this is an algorithm that solves the first match variant of the string pattern matching problem, and therefore also solves the decision version problem, because if there's no output, then that means the pattern does not occur at all. Okay, that's a naive algorithm, and its correctness is kind of obvious, right? So if the pattern occurs somewhere, then the algorithm will find that occurrence, the first occurrence. But so let's now move on to analyze the algorithm, which is here claimed to be asymptotically n times m. So to see why is it n times m, let's look at the loops. There are two nested loops, actually. There's one which is explicit, right, running from 0 to n minus 1. So this loop is executed n times. But inside there's another implicit loop, namely comparing this string to the rest of the pattern, right? So this is a substring, right? By the way, substring terminology. This is a substring of the long string. Compare this substring to this rest of the pattern. So together with this comparison, the zeros element of the pattern and the remaining elements of the pattern, this means that there are up to m additional comparisons, right? Up to as loop body for the outer loop, so that the inner loop is executed at most and up to m times. The outer loop is executed n times, resulting in a total number of computational cost of n times m. Right, and the question following our paradigm is whether this is optimal, right? Is this optimal? Well, let's look at the input size to answer that question, right? The input size is n characters for the long string and m characters for the pattern, so that the overall input size is n plus m, whereas the running time is n times m. So it seems that there's at least information theoretically, there's a possibility for improvement, right? There's a gap between the input size and the running time and the output size anyway, also because we're considering here only the first match problem or the decision version problem of the, where there's not really much time to spend in the output. It's just one single output. So following our virtues of computer science, the question arises whether this naive algorithm is optimal, and it wouldn't be called naive algorithm. It wouldn't occur at all in this lecture if it were already optimal. End of the story, nothing interesting to happen. Yes, it is not optimal. It can be improved. And the improvement we're going to consider and understand on the next slide is the famous Knuth-Morris-Pratt algorithm. And but to motivate and see where there's a possible chance for improvement is by looking at the what happens if there's if the pattern matches only partially, right? So let's look at an example run of this naive algorithm on this input. So up to ABC, there's a coincidence, there's agreement, but then the next character disagrees. It's a D in the pattern, it's X in the input string, and that's a disagreement. And in this case, the naive algorithm would start over again, would reset the index in the pattern string, which this index has no name here, but anyway, would reset to the first position in the pattern, start over, and would reset the position in the long string in the text corpus to the second character, right? And that's something kind of, how to say, strange, right? Why would an algorithm reset the pointer to the second string, which the algorithm has already read previously as part of the comparison with a pattern, right? So the algorithm has already compared these two strings, has compared these two characters, these two characters, these two characters. When comparing these two, that means that the algorithm at that time has read that symbol. And having read that symbol, why would we design an algorithm anyway that to read that symbol again? This is kind of a computational redundancy, right? And same for the C, right? So our goal is actually to design an algorithm with a property that the index into the text body, into the long string, will never decrease. Let me say that again. The naive algorithm kind of, whenever there's a mismatch between long string and pattern, then it will reset both indices, that in the pattern and the index into the long string. And the latter, that is kind of maybe one way of looking at the inefficiency or possible opportunity for improvement in the algorithm. The new algorithm, the Knuth-Morris-Pratt algorithm, will never decrement the index, will never move back in the large text body, but only move forward. And this, well, it will sometimes reset the index into a pattern string. So, but anyway, this is the kind of a key idea for improving the naive algorithm. In the long string, only move forward, never move backward. And that will be the key to the efficiency improvement. Okay. So this is what happens in the naive algorithm: reset the pointer to the pattern in the pattern to the start, and reset the pointer in the third string to the second character, and then start over. But this resetting in the third string, this is something we want to really avoid. This happens only implicitly, to be fair, because I chose not to spell out this innermost loop. There's no index name occurring here, but it really happens implicitly here. So the idea is to only move forward in a new algorithm that only moves forward in the long search string. Right. So yeah, let's continue the execution of the naive algorithm here. There's another apparent match here, but it's only a partial match again, because here's a disagreement on the X, here's a D, and then start over again, and so on. That's a kind of idea. Right. And for the improvement, the Knuth-Morris-Pratt algorithm that we'll see on the next slide performs actually some pre-processing on the pattern string before starting the actual search, before running through the long search string. And the pre-processing is something that we will indicate here, and I'll explain the meaning of the pre-processing in a minute. And it's kind of like an array that is underlies the pattern string. At each position of the pattern string, there will be an integer stored that points to another position in the pattern string. And here in this example, the pre-processing is the following. So if there's it's a substring pre-processing problem. I won't describe the pre-processing algorithm itself, but the pre-processing data structure. We're going to look at the longest common substring problem separately later. But here, the idea is that if we've already compared A and found A, B in the search string, right? So this is a pattern, and if already A and B has occurred, and then we see C also match D, and then there's another match A and B. And now if there's a disagreement here, which recall is exactly what happens in this example, then we already know that AB occurs also in the search string, right? So let me say that again. So this is our pattern string. The substring AB occurs twice here. And suppose that when matching the pattern, there was a partial agreement up to this AB, and then there's a disagreement, then intuitively we know that AB occurs in the pattern string here. And then we shouldn't reset and start again in the pattern string at this AB. We shouldn't reset the pointer, decrease the pointer by 6, right? From here back to 6 in the search string, but only decrease the pointer by 2 in order to start again at this position, because then we already know that this also occurs here in the pattern, okay? So the idea of Knuth-Morris-Pratt is to pre-process the pattern and create such a data structure. And this data structure is what I'm going to explain now. 0 indicates that when there's a disagreement at this position, then start over with the index in the pattern reset to the beginning. So if we find A occurrence in the search string, but the next string is not a B, then we should reset the index in the pattern to the beginning and check whether this symbol in the search string, which is not an B, happens to be an A, because if it happens to be an A, then we can resume our comparison for the rest of the string. Same here, this 0 indicates that if we have had a partial occurrence, A and B occur in the search string, but the next symbol is not a C, then we should start over again, not to decrease the position in the search string, but reset the position in the pattern to start whether this symbol, which is not a C, may be an A, and the next symbol may be an B. So 0 means reset the index in the pattern to the beginning and keep the current position in the search string. Let me say that again. There will be 2 indices, one for the position in the search string, note called K like here, and another index J for the position in the pattern. And when there's a partial agreement, A and B occur in the search string, but the next character is not a C, then keep the position in the search string K and reset the position in the pattern to see whether this third symbol, which is not a C, happens to be an A. Okay, and the improvement comes when there's a inter array, like in this case, entry 2. Let me explain this 2. 2 means we have already found an agreement up to here, the partial occurrence of the pattern in the search string up to here, but the next symbol is not a D. Then where should we resume in the pattern? Remember, we're not going to restart in the search string. The position in the search string will remain the same. But since AB has already been found in the search string before the disagreement happened, that means we don't need to start over. We should not start over again in the pattern from this AB, but we can start over here because we've already found that AB occurs in the search string, and only the third character was different. So we shouldn't start over in the pattern from here, but we can already start over just from here. That's the improvement, and keep the position in the search string. Now this is the meaning of entries in this preprocessing array. 0 means start over from scratch in the pattern. 1 means start over from the first position in the pattern. 2 means start over from this position in the pattern, and so on. Never decrease the index in the search string. But there's an additional entry in the preprocessing array, namely this -1. -1 means like 0, reset the position in the pattern to the start, but also increase the position in the search string, right? Remember, usually when there's a disagreement, let's say this character disagrees, then the algorithm will reset the position in the pattern and keep the position in the search string. But if there's a -1, then it means reset the position in the pattern and move on to the next position in the search string. Okay, that's intuition. That's a meaning of the pre-processing array of the pattern. Let me know, based on that, illustrate that with another example and with a Knuth-Morris-Pratt algorithm that you can see that makes use of this pre-processing in order to accelerate. So here, the pre-processing of the pattern looks at substrings, strings of occurrences from the initial segment. So here we have the initial segment ABA that occurs again, right? So here's ABA, and here's another occurrence of ABA. That means if the next character is a disagreement, then we don't start from scratch here in the pattern, but we start again here because ABA has already been read, and we only need to check whether the next character, which is not a B, happens to be a C, and continue from here with the matching. So this is what this arrow indicates. And similarly here, if we have here ABA, and then we should resume looking for the next. So if this is the end of the pattern, right? So if we get here, then it means we have found a match. And if we're looking for the next match, not start from scratch here, but start from scratch here, because we've already found ABA here. So, and similar here, if we have found, ABA here, yes, that's the same idea. So that in this case, the array during the pre-processing will be filled in this way. 0 means start from scratch. 1 means do not start from scratch, but start from the next character at position 1, that's the second character. 3 means start with a fourth character here, having already read ABA, and here having already read ABA. And -1 means, as you recall, not only start from scratch, but also move forward in the search string, whereas the ordinary 0 means keep the current position in the search string. So in that, with that example explained, we can now see here the Knuth-Morris-Pratt algorithm. So Knuth-Morris-Pratt has these two array indices, K and J, and the loop, the outer loop, as before, runs over all positions in the search string, in the long string, but now we will never decrease the array index in the search string. And the inner loop starts in the same way as previously. Check whether the first characters, the first symbols agree. Well, not the first symbols, but the J symbol in the pattern, right? That's a thing. Where do we resume searching in the pattern? And this is the index in the pattern where we start over. If they agree, then increment both pointers, both indices in the search string and in the pattern string. And if we've arrived at the end of the pattern, if J is M, right, then we have found an occurrence, right? And we output where that occurrence has started. So we're already at the end of the occurrence, so we should subtract the length of the pattern in order to output the starting position of the pattern in the string. So that's why there's a minus here. And then resume with the pattern index J according to this pre-processing array. Right? That's a thing. In the naive algorithm, we would start again from scratch, resetting J equal to 0, start from the beginning of the pattern. But now the improvement is to make use of the substring analysis of the pattern, namely if there's ABA and then there's a disagreement, then we already know ABA occurred and we don't start again from here, but we start again from here. This is what this index 3 means. In this case, J is equal to 0, is equal to 3, and then start over. The same happens if there's this is the case where there is a complete occurrence. So this is actually this case where J is this. The same happens if there's a disagreement, then also we don't start over from scratch in the pattern, but at the position indicated by the array. But now there's a special case, right? So the usual case is when the start over position is 0, or 1, or 2, or 3. In the first case, start from scratch. The second case, start somewhere in between in the pattern, but keep the position in the search string. Only if the entry in the preprocessing array is -1, is negative, then increase both indices, save one additional comparison because we already know that there's been an agreement here. So that's the Knuth-Morris-Pratt algorithm. And it's pretty subtle, this preprocessing array, how that is harnessed in the during the execution of the algorithm, and filling that array, performing the actual preprocessing is something we postpone to later when we talk about substring matching problems, substring analysis. So for now, what we want to do is analyze the computational cost incurred by Knuth-Morris-Pratt. So what is the computational cost? Well, again, we have this big outer loop, K, ranging from 0 to N. And the observation now is that K never decreases, right? So that's an important thing. Whereas J goes back and forth according to this array. And this means that the overall running time here, there is no, that's maybe the most important observation here, that Knuth-Morris-Pratt algorithm is not a nesting of two loops anymore, as was the naive algorithm. There's this outer loop, but since the outer index never decreases, there's no inner loop with the J index. The loop with over J is kind of implicit. It happens together with the outer loop. Whenever the outer index increases, then also the inner index increases. And if the inner index does not decrease, then the outer index remains the same or still gets to increase, so that the overall number of execution of the loop body is O of n plus m instead of O of n times m. And that's an improvement compared to the naive algorithm for the Knuth-Morris-Pratt. Okay, yeah, that's our first example string problem and its improved efficient solution using Knuth-Morris-Pratt. And observe that it solves actually all three variants of the specification: the decision problem, does the string contain, the first occurrence problem, and even the all occurrences problem. Maybe in this case, when it reaches the end of the pattern corresponding to this line in the pseudocode, then it will just continue searching for the next occurrence. And regarding the preprocessing, this is easily done in time O of m. So asymptotically, we can kind of ignore and drop that part. Good, moving on to the next string problem, the substring problem, longest common substring. So let's again follow our virtue or paradigm of stating the problem specification. And to this end, we fix an alphabet and we fix two strings. Now, yeah, this seems like the previous case, but here the strings are not necessarily of very different lengths. They can be of different lengths, but that's not the most important part. The question is, find the longest common substring which is common to both of the input strings. More precisely, find the length and possibly position of such a longest common substring. Here's an example instance of that problem. ABABC is the first input string, BABCA is the second input string, and observe that in this example, both strings have the same length, just for illustrative purpose. Then what is the longest common substring? It's BABC. It is a substring to both, right? BABC occurs here, BABC occurs here, and it is the longest. It has length 4, but there is, of course, no common substring of length 5 because the input strings have length 5 and they are not equal, so there cannot be a common substring of length 5. And that said, now here's a naive algorithm solving that substring problem naively by means, again, simply trying all possible combinations. So try all possible pairs of initial positions. Pairs that indicates quadratic running time, and this is exactly what's going to happen for the naive algorithm. So in imagining two loops, refrain from stating this as pseudocode. Imagine here these two loops, I and J, I running over all symbols in the first input string, J running over all symbols in the second input string. And for each such possible pair of input positions, compare the two substrings that start at these positions, compare the substring in the first string that starts at I, compare the substring in the second string that starts at position J, and see for how long they agree. And that means the running time is first n times m for the two loops over all possible pairs of initial and positions, times the running time for comparing for how long these two strings agree, and that in the worst case can be the minimum of the two string lengths, right? They could, this comparison, which is part of the innermost of the two nested loops, there's a third loop inside to compare these substrings for how long they agree. And that could take up to the minimum of the two lengths of the string, so that this is actually a cubic time algorithm, right? So initially said it's a quadratic time for the two nested outer loops, but there's a third loop inside implicit here, which raises the worst case computational cost to be cubic, and I leave it to you to create example instances, inputs, where this is really a cubic time algorithm. Maybe now we're looking at a for more efficient algorithm. Right, and the more efficient algorithm is using building a table. So this is called a dynamic programming approach. In the next section 7 of this course, we'll talk about general algorithmic paradigms such as divide and conquer or greedy or dynamic programming. And here we have dynamic programming underlying this algorithm. So if you don't know yet what dynamic programming is, don't worry. We're going to discuss this algorithm, and you will see implicitly or explicitly what dynamic programming really boils down to. So the idea of this algorithm is to create and gradually fill a table, a two-dimensional array, which is here called LCS, as abbreviation for longest common substring. So, and the meaning of the table entry, right? So we're supposed to output the longest common substring of the input strings, the two input strings, and the idea is to solve this problem first for initial segments of these input strings and to gradually grow the solution for the initial segments of these strings. So here's the idea. So the entry I, j should be the length of the longest common suffix of the following substrings, namely of the initial segments of the string. So if we look at position I, j, that means we won't consider the entire string v, we won't consider the entire string w, but only the part up to position I-1, that is of length I. And here we won't consider the entire string of length m, but only the first j symbols up to index j-1, and determine the length of the longest common suffix in these initial segments, right? So the length, not actually the longest common suffix itself, but the length. So there's several subtle but important points, aspects to point out here. Namely, first, here we're talking about suffixes. We're talking about initial segments of these strings, and we're talking about longest common suffixes. Okay, and these suffixes, this is what kind of makes the that will help us to actually fill that table. And let me emphasize the second thing is what we're actually interested is we're looking for the longest common substring, not for the longest common suffix, right? That's a difference. Here where original problem specification is for the longest common substring, and the algorithm fills this table with longest common suffix, okay? And of course, once we have filled that table, then by searching the table will give us the answers to the longest common substring, because the longest common substring that starts anywhere and ends anywhere is equal to the longest common suffix that starts somewhere and ends at some position I, j, which is therefore in the table. Let me say that again. Longest common substring may start somewhere and may end somewhere. Longest common suffix must start somewhere, but run until the end. But the trick is to consider all possible ends in this table, and considering all possible endings of the longest common substring means considering all common suffixes up to positions up to the position I, j of the initial segments. Does it make sense? So it's the same again. Longest common substring is the same as longest common suffix for some initial segment, and therefore we consider all possible initial segments in this table, and the length of the longest common suffix is there. So the message here is once the table has been calculated by our algorithm, then simply running through the table and taking the largest entry, right? So the entries in the table are integers, taking the largest entry, that's the answer to the original problem. Here's an example, right? So here are again two input strings, ABAB and BABA. Now, what is the length of the longest common substring? Where there are two possible answers, right? ABA is a common substring of length 3, but BAB is also a longest common substring, also of length 3. So the length is unique, but the strings themselves need not be unique for this problem, for the longest common substring problem. Now let's look at the table that the algorithm will create and fill with this meaning of the entries in the table. So here's the table. Let me explain that entry here, for example, right? So that entry means look at the initial segment ABA and here the initial segment BA. That's what this entry means. BA here and ABA, not the entire string, but only initial segments running up to the positions indicated by the array position. And then what is the longest common suffix of these two initial segments? What is the longest common suffix of ABA and BA? Well, that's BA. BA occurs in both as suffixes, right? Not as substrings, well, in particular as substrings, but as suffixes, because we only consider the initial segments up to this position, BA and BA, and therefore the length of the longest common suffix is 2, and so the entry here is 2. And so on. Similarly, here, let's consider this entry. This means consider the initial segment ABAB, which is actually the whole string, and consider the initial segment B, which is just the first string, and look at the longest common suffix. Longest common suffix is B, has length 1, and therefore the entry is 1. Here the entry is 0 because ABA and B, they do have a common substring, B, but they do not have a common suffix. This one ends in A, this one ends in B. That's a difference. And finally here, this example 3, consider the initial segments ABAB, entire string, and BAB, initial segment excluding the last character. They share the suffix BAB, which is a suffix, not a general substring, but a suffix of length 3. And so from this table, as indicated here, one can immediately read off the answer to the longest common substring problem, not the longest common suffix, but the longest common substring, because a substring is the same as a suffix of some initial segment, and that's why the table considers all possible initial segments. So reading off the table, the maximal value, which happens to be 3, will be the answer, and that's correct, right? The longest common substring here of these two have length 3, ABA occurs here, and BAB also occurs here, which is also even reflected by the table with these two occurrences of the number 3. So every occurrence of that maximum entry in the table actually also gives indicates where and what is the longest common substring. If the maximum value occurs repeatedly, as in this case, it means that the longest common substring occurs repeatedly. Good. And now that the meaning of the table has become clear, we can proceed to discuss how to algorithmically fill that table, right? So yeah, designing a dynamic programming algorithm is actually, how to say, it's challenging. It requires creativity, and maybe 2 steps. First step is to conceive what should be the meaning of the table. What information should be stored in the table? And the next phase is to design an algorithm that fills that table, that provides the entries of the table. And that's where we're at now. We've discussed the meaning of the table. First idea, this meaning. Talk about longest common suffixes instead of longest common substrings, but talk about many longest common suffixes instead of one common substring. And now we're going to fill the table. And the popular way of filling a table algorithmically is by first filling the top row, then filling the left column, and then gradually moving our way inside the table. This is kind of like also Pascal's triangle, right? Pascal's triangle has ones on its left, on its column, ones on its top row, and the entries in between are the sums of previous entries that are either left or up of the current entry. And that's what we're going to do here as well. So the top row will be indicated with, will be filled with zeros. This is not even reflected here in this example. We've saved these rows of 0 Why is that 0? Because that's the longest common suffix that is shared by the initial segment of length 0 of the string. So of course, when the first string or the first initial length segment has length 0, then there is no chance to have a non-trivial common suffix with an empty string. And same here for the left column. If the initial segment of the second string is empty, then also all common suffixes are empty and have length 0. So that for that purpose, imagine that there's another row of zeros on top here, and there's another column of zeros to the left here, which we have refrained from drawing because it's not really interesting pedagogically, but algorithmically, of course, the algorithm has to create that table. Okay, and once the top row and the leftmost columns have thus been filled, let me refrain from turning this equation into pseudocode, right? It's just an array over J here and an array running over I with an overall cost of n plus m, right? Then the interesting part really happens when we fill the inner entries of the table. So the inner entries are filled here inductively. The I plus first and J plus first entry of the table here depend on the ith and jth entry, which means one up and one to the left. One up and one to the left. And so if this entry means the length of the longest common suffix of the initial segments up to I and up to J, and if the position I at position I and at position J, which is a position beyond the current initial segment, right? This initial segment go up to position I minus 1 and J minus 1. And here we look at the next position, the ith and the j's. And if these two also agree, then that means that we have a longer common suffix for this new extended initial segments, right? These extended initial segments have a longer common suffix, longer by 1, namely this addition also agrees. Whereas if these two disagree, then we have no common suffix at all, right? Because common suffix means that also the last, in particular, last entry of that suffix must agree. But here, according to hypothesis, we're in the case where the two disagree, and therefore the next entry will actually be a 0. We see that happening here in the table, right? So let's look at that. For example, this entry here, the last character in this suffix BAB and ABA disagree. Therefore, they don't share any common suffix. That must be 0. Whereas this entry here, entry 2, is based on the observation that we already have an entry 1 here. The longest suffix of B and AB is 1. And the next character, A and A here agree, right? Here's A and here's A. So that means when we now consider the extended suffix, ABA here and BA here, then those agree up to length 2, which is longer. Add 1 to this entry. This is what this mathematical statement says. And now we can easily turn these mathematical statements into algorithms, namely into loops, right? Here we have 2 nested loops, one over I and one over J, in order to implement that. And in the loop body, perform this comparison, if this or if this, and then enter the next entry into the table, either this one or this, depending. So that the running time of the algorithm, which I don't even state here, but which arises immediately from these mathematical equations for the inductive definition of the table, is n times m. And this is the improvement to the previous naive algorithm, right? Remember, the previous naive algorithm had a cubic running time, that there was another factor of minimum of n and m. But here it's just n times m and no additional factor. So that the running time here is n times m, improving the previous from cubic to quadratic running time. So that's the message of this slide, an improved algorithm for the longest common substring problem. And following our virtue of computer science, now that we have analyzed an algorithm and with improved running time, we should ask the same question again as always: is this optimal or not? Is this optimal? Well, let's again look at the input size as a guidance towards information theoretic lower bounds. So the input size here has length n, this has length m, so that the overall input size is n plus m. And the running time here is n times m, which is already better than the previous naive algorithm, which had cubic running time, but still it's quadratic. And the question thus arises, is there a linear time algorithm? And it turns out that there is a linear time algorithm, an algorithm which has running time n plus m, but this algorithm is beyond the scope of the current lecture CS300 Introduction to Algorithm. It employs, it grades, fills, and uses a so-called suffix tree, an advanced data structure which is covered in a separate course, either data structures or advanced algorithm CS500. So this is our outlook, that the algorithm we've just seen using dynamic programming is already a considerable improvement from cubic to quadratic, but there's even a further improvement possible from quadratic to linear, which is not covered by this lecture. Okay, so next problem we're going to consider, but due to time constraints, we'll not be able to finish, is the edit distance problem. So let me introduce the edit distance problem. Edit distance also involves two finite strings as input, strings of length n and m respectively. And the goal is to convert the first string into the second string gradually by inserting and deleting operations, symbols from the first string in order to arrive at the second string. Here's an example. Let's suppose that the first string is kitten and the second string is sitting. How can we convert kitten to sitting? Well, there's always the naive way of first deleting all characters of the first string. So that means deleting 6 characters, gradually deleting K, I, T, T, E, N. We have to indicate at which position the symbol has to be deleted, not the symbol itself. So deleting T is not an operation, but deleting the third character, that's an operation. And deleting the entire string thus costs 6 operations. And then we can gradually insert the characters from the new string, sitting, which has length 7. So gradually inserting S, I, T, T, E, and G costs kind of 7 insert operation, resulting in a total of 6 plus 7, 13 operations. And that is possible for any pair of strings, right? We can take the first string of length n, gradually delete every symbol, that's n delete operation, and then gradually insert any other symbol m symbols of length that has an overall cost of n plus m for converting the first into the second string. That's always possible, but the edit distance is defined to be the minimum number of such insert and delete operations. So the question is, can we convert kitten into sitting using less than 13 insert and delete operations? And yes, indeed we can. We can do that with only 5 instead of 13 operations. What are for the 5 operations? First, we delete the K from kitten, resulting in itten. Then we insert an S, then from sitting, arriving at sitten. Then we delete the E, sitten, arriving at sitten. Okay. And then inserting another I here, resulting in sittin. And finally, appending a G, resulting in sitting. So that's 5 operations, right? 5 insert and delete operation. And I leave it to you to verify that it's not possible to convert the first string to the second using only 4 editing operations. There are various ways of doing it with 5. This is one way of doing it with 5. We can change the order of many of these insert and delete operations and do many other things. But generally speaking, it's 5 operations in various ways, and that's optimal. We cannot do it in 5. So in this case, the answer, the required output would be 5 is the edit distance of these 2 strings. Now the algorithmic question is, how can we do that in general? How can we assign that task to an algorithm? And that question can be solved, but first let me put some mathematical perspective on this problem. As you know, mathematics is crucial to many efficient algorithms in computer science. And the observation here is that the edit distance actually constitutes a metric on the set of finite string pairs. Remember, the 3 axioms of a metric say that first, the distance of any 2 different strings must be positive and the distance of 2 equal strings must be 0. That is satisfied, right? So 2 equal strings, converting one into the other requires 0 edit distance, and any distinct strings have positive edit distance. So that's one thing. The next thing is the triangle inequality. So the edit distance from one string to the second and from the second to the third is always greater or equal to the edit distance from the 1 to the third. And finally, there's the symmetry. The edit distance from V to W is the same as the edit distance from W to V. And I'd like to ask you to verify that, and that may be our next session's quiz. But for now, let's wrap up this session and recall what we've learned so far. So we've discussed about string problems. We've discussed the Knuth-Morris-Pratt algorithm, which is an improvement algorithm for pattern matching that improves over the naive algorithm from quadratic to linear time. And we've discussed the longest common substring problem, where the naive algorithm has cubic running time. And we've devised and analyzed a dynamic programming algorithm for that problem, incurring quadratic running time. We did not discuss, but only mention a linear time algorithm for that problem. And next time we're going to resume the edit distance problem and devise, again, dynamic programming algorithms for that problem. So that's all for today. Thank you very much for your attention, and see you next time.